Welcome to Section 2, where we will cover Symmetric Key Cryptography Part 1. In the first video, we will discuss how we can achieve confidentiality using symmetric key cryptographic algorithms. We consider two parties, Alice and Bob. Alice and Bob would like to have confidential communications over a non-secure channel, a channel where messages can be intercepted by an adversary. We assume that prior to this setting, the parties had some setup phase where they exchanged some key K. One of them, let's say Alice, generated randomly the key K and distributed its value through a confidential channel to Bob. How can we have such confidential channel? For example, Alice and Bob met physically, and Alice told Bob the value of K. Now that the key was already distributed, the parties do not need to rely anymore on a confidential channel to have secure communications. Using encryption, they can transform a non-confidential channel into a confidential channel. Let's see how they do that. We denote by P the plaintext that Alice would like to send to Bob. Alice applies an algorithm called encrypt that takes the plaintext P and the key K and outputs a ciphertext C. Alice sends the ciphertext C to Bob that applies an algorithm called decrypt that takes the ciphertext C and the key K and outputs the original plaintext P. Functionally, what we expect from encrypt and decrypt algorithms is when we apply decrypt over the ciphertext and we use the same key K, we obtain the original plaintext, what we can also express mathematically using this equation. From security point of view, we expect that an adversary that intercepts the ciphertext cannot retrieve P or get any partial information about P. This is the confidentiality guarantee. The symmetric aspect comes from the fact that the same key was used for encryption and decryption. This will not be always the case with cryptographic algorithms that we will see in this course. Let's now see some concrete examples of these algorithms encrypt and decrypt. This is our first symmetric crypto algorithm, Vernam Cipher. The term cipher just refers to an algorithm for encryption and decryption. Vernam encrypt and decrypt use the operation XOR, exclusive OR, that we can have on bits or bit strings. Those who are not familiar with this operation can stop the video and take the time to look at the yellow box below. To encrypt, Alice XORs the plaintext P with the key K. To decrypt, Bob XORs the ciphertext C with the key K. The functionality aspect is guaranteed by the following property of XOR operation. When we XOR with the same value twice, it is cancelled. So when Bob XORs with K, he obtains the original plaintext P. The security comes from the fact that an adversary that does not know the value K and intercepts P XOR K is unable to compute P. Let's see Vernam Cipher in action on a given example. Alice wants to encrypt the message hello using the key enigma. Before encryption, Alice must apply some encoding. She has to change the representation of her message hello to a format that is compatible with the cipher. Alice converts each character of her message to its ASCII code represented in hexadecimal. Example, the uppercase H is encoded to 48, the lowercase e is encoded to 65, etc. Alice has also to encode the key enigma. As you see, the uppercase e was encoded to the value 45, the lowercase n to the value 6e, etc. You might have noticed that the key enigma contains 6 characters, while our plain text hello contains only 5 characters. That's not an issue. We will only use 5 characters of the key and we will not consider the last character of the key. Now the encryption algorithm is applied by XORing the plain text with the encoded key to obtain the ciphertext, which is the sequence 0D, 0B, 05, 0B, 02. And this value is sent to Bob. Bob applies the decryption algorithm and obtains the sequence 48, 65, 6C, 6C, 6F. This was exactly the encoded representation of hello. Obviously, when Bob further applies the decoding, he obtains the message hello. Just a remark, keep in mind that the encoding and decoding do not provide any security. They are just here to change to a representation that is compatible with the cipher. Let's now see the advantages and limitation of Vernam Cipher. From security point of view, Vernam Cipher is a secure cipher. It provides perfect secrecy, as each plaintext character is encrypted using its own key. From implementation point of view, Vernam is very fast, as XOR operations are very efficient. And it requires little memory because the encrypt-decrypt algorithms process a single character at a time. An important warning is that the key cannot be used more than once. If we use the same key K with 2 plaintexts P1 and P2, the adversary that encrypts their corresponding ciphertexts C1 and C2 can XOR the ciphertext to obtain the XOR of the plaintext. So even that the adversary did not fully retrieve the plaintext P1 and P2, she obtained some partial information about these plaintexts. So instead of single key, the two parties require to have a key stream generator. For example, if we go back to Alice and Bob, if Alice wants to send the message, hello, meet you at 5 p.m., then she needs to use different keys for every word of her message. For illustrative purposes, we are using meaningful words for the key, like here, Enigma was a German cipher. But in real systems, we can use non-meaningful keys. Any combination of characters is fine. It's even better from a security point of view, as such keys will have high entropy. Means the number of possible keys is higher if we don't have a constraint of meaning. In general, Vernam Cipher is convenient for applications where the amount of data is unknown or continuous, like in network streams. Vernam Cipher is part of the family of stream ciphers. Stream ciphers are based on generating an infinite key stream and use that to encrypt 1 bit, 1 byte, or 1 character at a time. These ciphers are generally very efficient but come with a requirement of the stream setup, which is not possible in many applications and can be subject to vulnerabilities if it is not implemented correctly. In the next video, we'll look at another family of ciphers, the block ciphers. These ciphers work on larger chunks of data at a time. Even though they involve more complex operations, they are quite versatile and can be used for different use cases, to encrypt files, or within a request-response protocol such as HTTPS, and in many more applications. So see you in the next video.